Okay. Now we know that the multiple choice are what gets us pretty much every time. So let's analyze some gravitational problems. Okay. Now for this one, we're going to identify the type of force which causes whatever our bold-faced object is to travel in a circular path. We have these choices: gravity, normal, tension, applied, friction, spring, electrical, and magnetic. Now, ladies and gentlemen, if this is on a multiple choice test, we have not covered magnetic yet, so we're just going to kind of ignore this one. We haven't covered electrical either. Have we covered spring? No. We've covered gravity, normal, tension, applied, and friction. Okay, so an eraser is tied in a string and swung in a horizontal circle. So it goes like this. Now, what's making the eraser move in a horizontal circle? It's the tension of the string. Tension. All right. T-N-S-I-O-N. Can't spell today. All right. So for an object on a string, tension causes it to travel in a circle. What about a moon orbiting? Well, that's the situation where we have two objects, M1 and let's call mass of the moon orbiting around. Whenever we start going celestial, we tend to be talking about gravity. This is F big G, which is big G, M1, M2 over R squared. So this answer is A. Now, a car makes a sharp right-hand turn along a roadway. Whenever we talk about cars on roads, we're always talking friction. Okay, so the answer here is E, friction. A roller coaster passes through a loop. Let's look at the roller coaster at the bottom of the loop. Okay, there's going to be a normal force, Fg. Now, when it's at the bottom of the loop, what force is making it go toward the center? Well, what's the only force we have acting toward the center? That's got to be the normal force. So my answer here is B. Are you surprised? Okay, which of the following statements are true about gravity? What I'm going to do is I'm going to highlight the ones that are true and X out the ones that are wrong. Okay, gravity only acts between very, very massive objects. Well, no, it acts between all objects, not just massive ones. The gravitational force between an object and the Earth is inversely related to the distance between the object and the object center. Okay, so F is going to be G M1 M2 over R squared. So inversely related would be 1 over R. So this one is not correct either. It is inversely related to R squared. So not correct. The gravitational force can always be accurately calculated by multiplying the object of mass and the acceleration due to gravity. Well, yeah, that's kind of what we do, isn't it? So I would say this one is true. Let me highlight it. The gravitational force of acting upon an object is the same as the weight. Yes, as a matter of fact, that's true. The gravitational force is the weight. The gravitational force between two objects is independent of the mass of the smaller of the two objects. Oh, you know that's not true because Fg is G M1 M2 over R squared. It doesn't say anything about larger or smaller. If object A is gravitationally attracted to B with a force of X, then B will be also gravitationally attracted with X newtons. Well, of course that's true. This is Newton's third law. Action, reaction. So this is true. The doubling of the separation distance between objects will have the gravitational force between two objects. No! Fg is G M1 M2 divided by R squared. So let's look at this. If I have, let's see, if I double the distance, that's going to be 1/4 the force of gravity. So that's not true. If an object is placed 2 Earth radii above the surface of the Earth, then the force of gravitational attraction between the object and the Earth will be 1/4 the magnitude on the Earth's surface. No. And this is going to take a little bit of work. Fg is G m1 m2 divided by r squared. So let's look at this. At the surface, that's true. When we're 2 Earth radii above the surface, okay, I'm going to change colors here. So above the surface, we're talking about r is 3. The new radius is 3r. So Fg is going to be G m1 m2 divided by 3r squared. So it's going to be 1/9. Now this is an excellent multiple choice question. Be careful with it. Orbiting astronauts do not experience the force of gravity. This explains why they feel weightless. No, this isn't technically true. Technically what happens is the forces are balanced. This isn't a real good question. I wouldn't give this as a multiple choice question because this is a little confusing. Basically, they do get far enough out, they don't feel the force of gravity. So, I would say this one could be true or false, but basically false. And the reason it's false is nothing is ever outside of the force of gravity. Okay? It's proportional 1/r squared. You can get really small, but it never goes to 0. All right, which of the following is true about the acceleration of gravity? Identify all that apply. The acceleration of gravity experienced by objects near the Earth depend on the mass of the object. Nope, gravity is gravity. Remember, Fc is equal to Fg. So mv squared over r, which is my centripetal acceleration, which is equal to mg, has to equal g m mass of the planet divided by the radius of the planet squared. So the gravity they feel depends only on the planet. Not true. The acceleration of gravity experienced by objects near or far from the Earth depend upon the mass of the Earth. Well, yeah, that one's true. Clearly, a more massive planet will have a larger gravity. The acceleration of gravity experienced by objects near or far from the Earth is inversely related to the distance between the center of the object and the center of the Earth. Technically, this is not true. Because why? G is big G, the mass of the planet, divided by the radius of the planet squared. So it's proportional to 1/r squared. This is a trick question. Increasing the mass of an object will increase the acceleration of gravity experienced by that object. No! G is always going to be big G, mass of the planet, divided by the radius of the planet squared. The mass of the object doesn't matter at all. Doubling the distance between an object and the Earth's center will decrease the acceleration due to gravity by a factor of 4. Let's see. G is big G, mass of the planet, divided by the radius of the planet squared. So, if I double the distance, I'm going to change color here. So if I double the distance, 2 squared, so this is going to be 1/4. All right, yep, this one is true. Doubling the distance will indeed decrease the gravity by a factor of 4. The acceleration of an orbiting satellite is equal to the acceleration of gravity at that particular location. Yes, that's what we've been saying all along. Excellent. If the mass of the Earth were doubled, then the acceleration due to gravity on the surface would be about 20. Well, let's look at the numbers. Okay, G is G, mass of the planet, divided by the radius of the planet squared. If the mass were doubled, all right, then gravity would be about 2G. Well, G is about 9.8, so this would be 19.6. What do you say? Is that close to 20? I would call that pretty close to 20. If the mass of the planet were doubled and the radius of the Earth were doubled, then the two would offset each other and the acceleration of gravity would still be about 10 meters per second squared. Okay, this one's not true. Let's see why. Let's go back. G is G, mass of the planet, divided by the radius of the planet squared. Let me change colors here. Now, if the mass is doubled, so it's going to be twice the mass, and the radius were doubled. The radius is doubled. This would be 2 divided by 4 times G, or it'd be about half G. So this one's not correct. Don't you just love multiple choice questions? You got to.